try to do some examples that might help you in the exam, or at least give you a revision of the section that you could potentially use for the exam. Okay, so the first question I'll do is problem set 9, question 13, which says, oh, if prove uh, prove that if f is continuous, and f of x is equal to 0 for every x in A, which is a dense set, then f of x is equal to 0 for every x. Okay, proof. Suppose there exists x1 such that f of x1 is not equal to 0. Okay, so because f is continuous, as f is continuous for epsilon is equal to absolute value of f of x1 over 2, there exists a delta greater than 0 such that x1 minus x smaller than delta implies f of x1 minus f of x smaller than epsilon, right? That is by definition of continuity. So now, as A is dense, there exists a x naught such that absolute value of x1 minus x naught is smaller than delta, right? This is the definition of dense, that given any point x1, you can always, at any distance delta, you can find an x naught within that distance. Given any open neighborhood around any point, you should always be able to find some point of A inside it, right? So x1 minus x naught is smaller than delta, therefore f of x1 minus f of x naught is smaller than epsilon, which is equal to absolute value of f of x1 over 2, right? But x naught belongs to A, there implies f of x naught is equal to 0, right? And therefore f of x1 is smaller than f of x1, absolute value of x1 over 2, which is a contradiction. D-I-C-T-I-O-N. Yeah. Contradiction. And therefore f of x1 was indeed equal to 0, and therefore f of x is equal to 0 for every x, as required. Okay. The next question I will do is again question 13 from problem set 10 this time. Okay, which is to say, suppose f of x is equal to x squared if x is rational, and this is 0 if x is irrational, which is r minus q, right? Then show that f is differentiable at 0. Prove f is differentiable at 0. Proof. Here's how you prove f is differentiable at 0. We want to show want to find limit h goes to 0 f of 0 plus h minus f of 0 over h, right? Now, f of 0 is equal to 0, therefore want f of, limit h tends to 0, f of h over h, right? Does this limit exist? Does this limit exist? Right? So, well, we want to show that actually it exists, right? So now, if h is irrational, f of h is equal to 0, therefore f of h over h is equal to 0, right? In every case where h is irrational. So, therefore, we want to show limit h goes to 0, f of h over h is equal to 0, right? So what we are going to do is we want to show this, well, this is trivial if when I'm looking at h irrationals, but I want to show that this limit is 0 even for rationals tending to x, tending to 0. Let xn n is equal to 0 to infinity be a sequence of rationals such that limit n goes to infinity xn is equal to 0, right? This is any arbitrary sequence. So if I show that the limit of the derivative, so if I show that f of h over h for this sequence is 0, that would mean, oh, the limit is 0 for rationals as well as irrationals, and so this is 0, right? So what I'm going to do is, therefore, limit h goes to 0, limit n goes to infinity, f of xn over xn is equal to limit n goes to infinity xn squared over xn is equal to limit n goes to infinity xn is equal to 0, right? Well, this is given any, therefore limit h goes to 0 f of h over h for any sequence of rationals is equal to 0, right? Therefore, the limit is 0 for rationals, therefore limit h goes to 0, f of h over h is equal to 0, and therefore derivative exists at x is equal to 0, derivative of f exists at 0, and f is differentiable at 0. Oops. Okay, let us now look at an example from problem set 11. Problem set 11. I'm going to do question 10. It says if fn of x is equal to x to the n and 0 smaller than or equal to k smaller than or equal to n. Oops. Prove by induction that fn, the kth derivative, which is generally written this way, of x is equal to n factorial over n minus k factorial x to the n minus k is equal to k factorial, choose k times x to the n minus k. Well, the fact that n factorial over n minus k factorial is exactly equal to k factorial and choose k is trivial. So I will just show this part. Okay. You have seen that this is equal to the right hand side before. Proof. Well, you can show that for this result, this result holds for every n. We are going to show it in induction on k. I need to show that for every n. Well, whatever. For base case, k is equal to 1. Fn1, which is the first derivative of x, is equal to d over dx of x to the n is equal to n x to the n minus 1, which is equal to n factorial over n minus 1 factorial times x to the n minus 1, right? Therefore, base case checked out. Therefore, holds for k is equal to 1. Now I want to show it for any general k. Assume true for k, show for k plus 1, right? So the k plus 1th derivative of fn is actually just d over dx of the kth derivative of x, right? Is equal to d over dx of, by my assumption that it is true for k, n factorial over n minus k factorial times x to the n minus k. Well, these are constants. N factorial and n minus k factorial are constants with respect to x, so they come out. N factorial over n minus k factorial d over dx of x to the n minus k, which is equal to n factorial over n minus k factorial times n minus k x to the n minus k minus 1, which is equal to n factorial over n minus k plus 1 factorial times x to the n minus k plus 1. Therefore, this holds true for every k. Therefore, holds for k plus 1. Therefore, holds for every k in 1 to 0 to n, 0 dot 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 n. Okay. Well, I didn't show for 0. Maybe I should have showed for 0. Well, at 0, it is exactly just the 0th derivative is the function itself. It is easy to see that it's exactly that. Okay. If you want to do the result for n to prove induction on n, base case n is equal to 1, well, what do we have? When n is equal to 1, I can have, well, I can show the result for any k, right? The result holds for any k. I will show for, since I've for k is equal to 1, f of the first derivative of n is equal, I'm not going to show this. This is really trivial. We have already shown that the derivative of x to the n is just, the first derivative of x to the n is nx to the n minus 1, and then you can just use k, derivative on k. That would be enough to show for everything. Okay, so I'm not going to show it for that. Okay, let me do one last example, which is from problem set 12. I will do problem 3. Okay, prove that if a0 over 1 plus a1 over 2 plus dot 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 plus an over n plus 1 is equal to 0, then a naught plus a1x plus a2x squared plus blah 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 plus an x to the n is equal to 0 for some x. Right? There is some x for which this is true. Proof. Let f of x is equal to a naught over 1x plus a1 over 2x squared plus dot 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 plus an over n plus 1 x to the n plus 1. Okay, then f of 0 is equal to f of 1 is equal to 0, right? F of 0 is 0 because every single term has an x. F of 1 is equal to 0 because if I plug in 1 instead of x, I get exactly this, right? F of 1 is exactly this. Great. F is differentiable as it is a polynomial, right? Therefore, by Rolle's theorem on 0, 1, there exists some x in 0, 1 such that f prime of x is equal to 0. Therefore, what is the derivative of f prime of x? F prime of x, which is equal to, well, derivative of x is just 1, a0 plus a1 times 2x over 2 plus dot 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 plus an over n plus 1 times n plus 1 x to the n is equal to 0, which therefore a naught plus a1x plus dot 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 an x to n is equal to 0, right? So we have found our necessary x. In fact, it's between 0 and 1 such that the value of a naught plus a1x plus dot 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 an x to the n is equal to 0.